test the convergence of summation n equals to 2 to infinity log n divided by n plus square root of n plus 1. So we take n equals to log n divided by square root of n plus 1. So the series can be written as summation n equals to 2 to infinity and now we consider dn equals to 1 by square root of n. So the limiting value of n by n equals to limit n tending to infinity n log n divided by square root of n plus 1 divided by 1 by square root of n equals to limit n tending to infinity, we get log n divided by square root of n plus 1 into square root of n. Taking this square root of n and square root of n plus 1, and then write log n, which is equals to limit n tending to infinity. N can be written as 1 plus n minus 1 divided by n plus 1 to the power half into log n equals to n tending to infinity divided both 1 plus n and 1 by n plus 1. So we get n plus 1 by n plus 1 minus 1 divided by n plus 1 to the power half into log n. This is equals to limit n tending to infinity 1 divided by 1 minus 1 by n plus 1 to the power half into log n. Now taking n tending to infinity. When n goes to infinity, then n plus 1 is also going to infinity. 1 by infinity goes to 0, and the altogether part 1 minus 0 goes to 1, and square root of 1 is 1. So first part is 1 into. Now when n goes to infinity, then it is clear that log n is also goes to infinity. So 1 into infinity, this becomes infinity. So the limiting value n is infinity. Now we use the comparison test. Now we use the comparison test. Comparison test, we know that when n equals to infinity, then summation n is convergent implies that summation bn is also convergent, and summation bn is divergent. This implies that summation n is divergent. Now here we consider bn as 1 by square root of n. So the series summation n equals to 1 to infinity 1 by square root of n is divergent by p-test, since summation 1 by n to the power p is convergent when p is greater than or equals to 1, and divergent when convergent when p greater than 1 and divergent when p less than or equals to 1. Now since here compare this with this, you see that here p is half and half is less than 1. So by p-test we say that summation 1 by square root of n is divergent. Now so in this case summation bn is divergent. So by comparison test we say that summation n is also divergent. Summation n means the original series. Summation n equals to 2 to infinity log n divided by square root of n plus 1 is also divergence, and this completes the solution. Next we consider test the convergence of the series summation n equals to 2 to infinity 1 by log of n. Now it is clear that log n is less than or equals to n for all n greater than equals to 2. This is we know. The value of log n is also less than or equals to n. You put some value of n from n equals to 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. In each case we see that these values also less than equals to the value of n, that is log 2 is less than equals to 2, log 3 is less than equals to 3, log 4 is less than equals to 4 and so on. From calculator we easily get this kind of expression. So in general we write this statement that log n is lesser or equals to n for any n which is greater than or equals to 2. So this, from this we have log n is greater or equals to 1 by n. Since we know that if this kind of inequality holds, then this must be true. But we assume that a and b are both non-zero quantity. So if we taking both side summation runs from a to infinity, we see that summation n equals to 2 to infinity 1 by log n is greater than or equals to summation n equals to 2 to infinity 1 by n. Now we know that summation n starting from 1 to infinity is divergent by p-test when value of p equals to 1. So this is divergent. Now summation n equals to 1 to infinity 1 by n is divergent. From this one can say that summation n equals to 2 to infinity 1 by n is also divergent. This is the minor change. Here you notice that the value of n starting from 1 and here the value of n starting from 2. Altogether series summation n starting from 1 to infinity 1 by n is divergent. So if we start from 2, that is when n equals to 1, we remove this part, then this part is also divergent. This part is also divergent since if we remove some finite part from an infinite series, then it does not change. Or rather we say that it cannot change the convergence or divergence of the series. This is the main cause. If we remove some finite quantity from an infinite series, then the nature of the series remaining same. If the series summation n equals to 1 to infinity 1 by n is divergent, now we remove the finite part, that is the series also can be written as put n equals to 1, this means 1 by 1, and taking all the remaining portion same. So this expression summation n equals to 1 to infinity 1 by n also can be written as 1 plus summation n equals to 2 to infinity 1 by n. Now from P series we know that this part is divergent and 1 is a finite term. Then if we remove the finite term from the infinite series, then the nature of the remaining series, that is summation n equals to 2 to infinity 1 by n, then it is also remaining same, that is it is divergent. So summation starting from n to n equals to 2 to infinity 1 by n is also divergent. So we say that summation n equals to 2 to infinity 1 by n is also divergent. Now this part is divergent and the series this is greater than or equals to a series which is divergent. So from this we easily say that the original series summation n equals to 2 to infinity 1 by n is also divergent, since it is greater or equals to a series which is already divergent, and this completes the solution of the problem summation 1 by log of n, which is divergent. Test the convergence of summation 1 by square root of n factorial. Now by the definition of factorial we have n factorial equals to 1 into 2 into 3 into 4 up to n. This is the definition of n factorial. Now 1, 2, 3, 4 and so on n, which is greater than or equals to, where total term is n term. So this is 1, 2, 3, 4 and n term, total term n. Now we change the term 2 is greater than or equals to 2, which is correct. Now 3 is greater than 2, so we replace in the place of 3 by 2, and 4 is also greater than 2 and so on. n is also greater than or equals to 2. If we assume that n is greater or equals to 2, so we place 2 for this 2, we place 2 for this 3, we place this 2 for this 2. In each case 2 is less than equals to 2, 3 is less than equals to 2 is less than equals to 3, and 2 is also less than or equals to 4. And in the same manner we replace n by n2, which is less or equals to n. So here total n terms, and we discard just one terms, and the remaining terms are n minus 1. Here total n minus 1 terms, since we left only with this one terms. So if we multiply this 2 into 2 into 2 up to n minus 1 terms, so this becomes 2 to the power n minus 1, and this is n factorial, which is greater or equals to 2 to the power n minus 1. So n factorial, square root of n factorial is greater than equals to square root of 2 to the power n minus 1, which is 2 to the power n minus 1 to the power half. So this is 2 to the power n minus 1 by 2. This shows that 1 by square root of n factorial is less than equals to 1 by 2 to the power n minus 1 by 2 for all n belongs to natural number. Now consider the series summation 1 by 2 to the power n minus 1 by 2 starting from n equals to 1 to infinity is basically is a series with common ratio ratio 1 by square root of n, which is less than 1. Common ratio means basically this is a geometric series. Common ratio means here nth term is 1 by 2 to the power n minus 1 by 2 and n plus 1th term is 1 by 2 to the power, just add one term here, n plus 1 minus 1 by 2, so this becomes 2 to the power n by 2. Now a n plus 1 by a n equals to 1 by 2 to the power n by 2 divided by 1 by 2 to the power n minus 1 by 2. This is 2 to the power n by 2 into 2 to the power n minus 1 by 2. This is 1 by 2 to the power n by 2, 2 to the power n by 2 into 2 to the power minus half. This and this cancel, and finally a n plus 1 by a n is 1 by root over 2. So this is called the common ratio, which is here, which is less than 1. So in this we can find the common ratio in case of geometric series. Now we know that in case of geometric series, if the common ratio is less than 1, then the series is convergent. Now summation n equals to 1 to infinity 1 by 2 to the power n minus 1 by 2 is a geometric series with common ratio 1 by square root of n, which is less than 1. Since root over 2 is greater than 1, we know that this value becomes 1.4 something, so it is greater than 1. So 1 by square root of n, 1 by root over 2 is less than 1. So this is a geometric series with common ratio 1 by root over 1 by square root of 2, which is less than 1. So this is a convergent series. So this is a convergent series, and 1 by square root of b factorial is less than equals to 1 by 2 to the power n minus 1 by 2. Taking summation both sides starting from n equals to 1 to infinity, this part is convergent, this total part is convergent series, then this is lesser than or equals to a series which is already convergent, and this series becomes, since n belongs to from the natural number, so this is greater than or equals to 0, and since this is convergent, so we say that summation n equals to 1 to infinity 1 by square root of n factorial is also convergent. Sometimes the ratio test is fails, then we consider another test which is called Rabi test. Here we discuss it. When we already know that limit n tending to infinity a n plus 1 by a n is 1 in case of ratio test, then we cannot conclude the convergence divergence of the original infinite series summation a. When we get 1 in the ratio test, then the test becomes fails, and we use the Rabi test. This is the statement of the Rabi test. Assume that summation n is a series of positive terms, and here we consider, in case of ratio test, L equals to a n plus 1 divided by 10, and in case of Rabi test, we consider L equals to limiting value of n tending to infinity n into a n divided by n plus 1 minus 1 equals to L, and when n is greater than 1, then the series is convergent. L is less than 1, the series is divergent, and when L equals to 1, then also the test becomes fails. That is, we cannot conclude any definite conclusion from this Rabi test. Now we use some in some problem this Rabi test when the when the ratio test is fails. Check the convergence or the divergence of the given series. This is the given series. Now we write the series as 1 plus summation an. N starting from 1 to infinity. The series also can be written as n, where n equals to, this is the first term, this is the second term, this is the third term, and so on. This is the first term, this is the second term, and this is the third term. Here in the numerator part, the terms starting from 1, so in the numerator part of n also starting from 1 into and in the denominator part the series starts from 2, so also in the n term, in the denominator part of the nth term is also starting from 2. Next number is 4, 6. In the third term, the last number of the denominator part is 6, which is 2 into 3, and in the second term the denominator part ends at 4, which is 2 into 2. Similarly, in this fashion we can write the general n term ends at 2 into the number of term, that is n. So this is the denominator part of the general term n, and we see that in each case, in the third term, numerator part is also just 1 less the last number of the denominator part, 5, 6 minus 1, 3, 4 minus 1, here 1, 2 minus 1. So in the general nth term n also ends at 2n minus 1, and the intermediate numbers are all odd numbers, 1, 3, 5 and so on, ends at 2n minus 1 into, in the first term, 1 by 3, which is 2 more than the numerator part, which is 1 here, last numerator part, here 3, and multiplied by the second term by 1 by 5, which is 2 more than 3, here 7, which is 2 more than 5. So here also, in this portion, we add just more 2, and we simplify this portion, we have 12 plus 1. So this is the general nth term. Now we find that an divided by n plus 1, which is, this is the nth term. So write first this, n plus 1 term, add, replace in each case n plus 1, replace n by n plus 1, or we say that replace n by n plus 1. In each case replace n by n plus 1. Here we replace n by n plus 1, then this becomes 2n plus 1 divided by 2, 4, 6 into 2n into, replace n by n plus 1, that is 2n plus 2 into, replace n by n plus 1, so 2n plus 2 plus 1, which is 2n plus 3. So after simplifying, Now cancel 2, 4, 6 up to 2n. 2, 4, 6 up to 2n. This is 12 plus 2. And here 1, 3, 5 up to 12 minus 1. 1, 3, 5 up to 12 minus 1. So in the numerator part, remaining term is 12 plus 2 and 12 plus 3. 12 plus 2 into 12 plus 3 divided by 2n plus 1 whole square. Here 12 plus 1 and here 12 plus 1. So this is the limiting value. Not limiting value, the ratio value n divided by n plus 1. So when we find this expression, limiting value of n divided by n plus 1, which is limit n tending to infinity, 12 plus 2 into 12 plus 3 divided by 12 plus 1 whole square. Taking common n from this part and also this part. Here n square. If we taking n common, the remaining portion is 2 plus 2 by n, and here 2 plus 3 by n. And if we taking common n, then it becomes n square. Remaining part 2 plus 1 by n whole square. Now cancel n square, n square. If we taking limit n tending to infinity, this part, and this part going to 0, and even part is 2 into 2 divided by 2 square means 4 into 2, which is 1. So here it is the drawback of the ratio test. So by ratio test tells here, since limiting value of the n divided by n plus 1 is 1, so here we apply the Rabi test. So we progress for the Rabi test here. This is n by n plus 1. So n by n plus 1 minus 1 equals to simplifying this portion. Normally This is the value of n divided by n plus 1 minus 1, 6n plus 5 divided by 2n plus 1 whole square. So n into this expression becomes n into this. Now the leading value of n into an divided by n plus 1 minus 1, which is L by Rabi test. This becomes limit n tending to infinity n into 6n plus 5 2n plus 1 whole square. Taking n common from this, we get n square into 6 plus 5 by n, and taking n common from this, n square into 2 plus 1 by n whole square. Cancel n square. When taking n tending to infinity, this part and this part going to 0, and the remaining portion is 6 divided by 2 square means 4, which is 3 by 2, and which is non-zero quantity and greater than 1. So we already discussed that n into an divided by n plus 1 minus 1, which is L, is greater than 1, then the series is convergent. Since L is greater than 1, so by Rabi's test, the series, this series is convergent. So the original series is convergent, which is one application of Rabi test. Now we discuss this example. The series can be written as one plus summation an starting from 1 to infinity, where an equals to, say this is the first term, this is the second term, this is the third term, and so on. In the first term, numerator part is only alpha, and next term in alpha plus 1, next term into alpha plus 2, so on. In case of third term, in the numerator part, in the last expression, this is alpha plus 2, which is 3 minus 1, and in case of second term, the last term in the numerator part is 2, which is 2 minus 1. So similar fashion, in the nth term, the last term is alpha plus n minus 1, and in the denominator part, which is very easy basically. Third term, last term is 3, 1 into 2 into 3, second term 1 into 2, first term 1, only 1. So in the nth term, in the denominator part, starting from 1 and ends at n. So n plus 1, alpha plus 1, alpha plus 2, and alpha plus replace n by n plus 1. First write this term and then replace n by n plus 1. So we know the previous term of the last term, which is alpha plus n minus 1, and in the last term is alpha plus n only. Plus 1 and minus 1 is cancelled here. So this is only the alpha plus 1, and in the denominator part, replace n by n plus 1, that is 1 into 2 into 3 up to last term is replace n by n plus 1, and the preceding term of the last term is n. So this is a n and this is n plus 1. So an divided by n plus 1, which is alpha plus 1, alpha plus 2, alpha plus n minus 1, alpha plus n divided by 1, 2, 3. This is an part. So the last term is alpha plus n minus 1, and this is up to n, and we divide it by an plus 1, that is which is this term, alpha plus 1, alpha plus 2, alpha plus n minus 1 into alpha plus n divided by 1, 2, 3 up to n into n plus 1. So divide alpha plus 1 up to alpha plus n minus 1, and here remaining is alpha plus n in the denominator part, and we cancel 1, 2, 3 up to n, 1, 2, 3 up to n, and remaining part in the numerator part is n plus 1. So this is the ratio, n plus 1 divided by alpha plus n. So an divided by n plus 1 is n plus 1 divided by n plus alpha. Now limiting value of an by n plus 1 equals to n plus 1 divided by n plus alpha. Taking common n, which is 1 by 1 plus n, and taking common 1 plus alpha by n, cancel n, and when n tending to infinity, numerator part goes to 1, denominator part goes to 1, 1 by 1 is 1. So also here the ratio test becomes fail. So we apply rabbit test. Now limit n tending to infinity n into n divided by n plus 1 minus 1 equals to limit n tending to infinity n into n divided by n plus 1 is n plus 1 n plus alpha minus 1. Cancel n tending to infinity n into 1 minus alpha divided by n plus alpha, divided both numerator and denominator part by n, which is 1 minus alpha and 1 plus alpha by n. Now when n tending to infinity, this goes to 0 since alpha greater than 0. So the remaining part 1 minus alpha by alpha, which is 1 minus alpha. Now alpha is greater than 0, so minus of alpha is less than 0. So 1 minus alpha is less than 1. So the limiting value of limit n tending to infinity n into n divided by n plus 1 minus 1 is less than 1, that is which is L. So L is less than 1. So by rabbit test the series is divergent since L is less than 1. So by rabbit test the series is divergent since L is less than 1 in this case. This is the complete solution of the problem. Next we consider another test, which is Cauchy's root test. Consider the series of positive terms n and assume L equals to limit n tending to infinity n to the power 1 by n. Now when L is greater than 1, then the original series n is divergent. This is number 1. When L is less than 1, the series is convergent, and when L equals to 1, then we cannot conclude any definite conclusion from this test, which is Cauchy's root test. Now we discuss some example of Cauchy's root test. Here we examine the nature of the series 2 square by 1 square minus 2 to the power minus 1. This is the first term. This is the second term, 3 cube by 2 cube minus 3 by 2 to the power minus 2. And this is the third term, and so on. So first we recognize the general n term. It is clear that when the first term power becomes minus 1, second term to the power minus 2, third term to the power minus 3. So in case of nth term, the power becomes to the power minus 3. In the first term, denominator is here 1 square, here 1, here 2 cube, here 2, here 3 to the power 4 and 3. So in the init term here n and n, this is obvious. First term 1 1, second term 2 2, third term 3 3. So init term n. Then the power. In the first term this is 2, which is 1 plus 1, 3, second term plus 1, 2 plus 1, 3. And in the third term 4, which is third term plus 1, 3 plus 1, 4. So in case of nth term, this is to the power n plus 1, and the numerator part, which is just one more than the number of term. In the first term this is 2, there is also 2, second term 3, just one more. So in case of nth term, numerator part just one more, n plus 1, n plus 1. The power is in the first term 2, so number of term plus 1. Third term, second term 2 plus 1, 3, third term 3 plus 1, 4. So in case of nth term, this is to the power n plus 1. And this is the general nth term. So now we start calculate. So L equals to limit n tending to infinity n to the power 1 by n. When in any problem we see that any power related problem is arise, something to the power n, some to the power n, or some to the power n minus 1. In case of power type problem, then we always apply the Cauchy's root test. Here an term is some expression to the power minus n. So when power arises, this kind of power, then we always, or in the maximum case, we apply the Cauchy's root test, otherwise not. Then tending to infinity, n to the power 1 by n. This is n plus 1 divided by n to the power 1 minus n plus 1 divided by n to the power minus n to the power 1 by n. This is equals to limit n tending to infinity to the power n into 1 by n, cancel n by n. So remaining portion is n plus 1 to the power n plus 1 divided by n to the power n plus 1 minus n plus 1 by n to the power minus 1. So simplify this expression. Limit n tending to infinity n plus 1 by n to the power n plus 1 minus n plus 1 by n to the power minus 1. So L equals to limit n tending to infinity 1 divided by 1 plus 1 by n to the power n plus 1 minus 1 plus 1 by n. Since you know that a inverse equals to 1 by n, so this expression to the power minus 1 divided by 1 divided by this expression. This also can be written as limit n tending to infinity 1 plus 1 by n to the power n plus 1 minus 1 plus 1 by n, taking limit in the denominator part, since in the numerator part this is 1. Now if we taking limit inside, then limit n tending to infinity 1 plus 1 by n to the power n plus 1 minus limit n tending to infinity 1 plus 1 by n. So limit 1 divided by limit n tending to infinity, this part 1 plus 1 by n to the power n plus 1 can be written as 1 plus 1 by n to the power n into 1 plus 1 by n minus limit n tending to infinity 1 plus 1 by n. Now taking limit both this part and this part, so this becomes 1 divided by limit n tending to infinity 1 plus 1 by n to the power n into limit n tending to infinity 1 plus 1 by n minus limit n tending to infinity 1 plus 1 by n. Now we know that here we use the result. We know limit n tending to infinity 1 plus 1 by n to the power n is e exponential whose value lies between 2 and 3. So this part becomes e. If we taking n tending to infinity, this goes to 0. So this part becomes 1, and also this part becomes 1. So we have 1 divided by, this is e into 1 minus 1. This is 1 divided by e minus 1. Now we already discussed that e lies between 2 to 3. So 2 minus 1 is less than e minus 1 is less than 3 minus 1. So 1 is less than e minus 1 less than 2. So 1 is greater than 1 by e minus 1 is greater than half. Basically this part is less than 1, which is n. So n is less than 1. So by Cauchy's root test we say that the given series is convergent since n is 1. So by Cauchy's root test we say that the series is convergent. So this is the complete solution of the problem, and in the next class we discuss about some more example of Cauchy's root test and the remaining results based on this chapter series.